Thanks for coming and giving us our time, valuable time. I'm Utkarsh Sharma. I'm currently working as a senior software developer with Astronomer. I'm particularly working in part of OSS team. As part of OSS team, we tend to manage OSS Airflow, develop new features around it, and also have our own version of Airflow, which works as a seed for our own products, right? So that's what we do. And a little bit about Astronomer. So we are a leading managed Airflow service provider. And basically, you just have to have your own DAGs, and we just give you all the tools that is required to run your Airflow instances on scale, right? And I'm going to be talking about DAG serialization, right? So any idea what DAG serialization would mean? Any thoughts?
So basically, it's the directed graph is serialized in memory to improve the performance. Okay. That's what I understand.
Yeah, partly true. Anyone else? Okay, how many people have used Airflow earlier? Okay, so you consider yourself beginners or advanced users? Medium? Okay, cool, awesome. So what I mean by DAG serialization here is, so what serialization means, right? Serialization is basically converting a in-memory object to a form where you can pass it on network or save it in a file, right? So this is precisely what happens. So when you as a user give DAG to Airflow, it needs to be stored in database, right? So that it can be worked upon by Airflow, right? So that's what DAG serialization is. Little background about why this talk is in place. So my motive here is to basically, help users who actually wants to contribute to Airflow's code base, right? And if you go into any of the companies, so basically once you get a project, you are basically given one subject matter expert that will walk you through the project. And that person will guide you and tell you what all projects, what all tools and technologies been used there, right? So there is one person who bridges that gap when it comes to any of the project. But when it comes to OSS, you usually when it comes to OSS, you usually don't have any such person, right? Because it's an open source tool, and there is no one who can guide you through the code. Right. So the intent of this talk is to actually help with bridging this gap. So I'm going to be covering a DAG serialization, which is the initial bit when someone starts Airflow, right? Without further ado, so the responsibility of DAG serialization, right? Basically, we discussed one thing, right? So it needs to basically convert a Python file, which is a DAG file, into an in-memory object, right? So that's one of the responsibilities of DAG serialization code base. Second responsibility of DAG serialization code base is basically you would also need to handle callbacks. Now, this is a bit of a surprising here because why DAG serialization is concerned with callbacks, right? Callbacks and agent signals. So I come to more details about DAG callbacks and agent signals there. So that's one of the responsibility. Other responsibility is reporting errors. So what, as a user, if someone has created a DAG, right? If there is an import error or some other error that you made in Python file as a user, you need that error to be reported back to the user. So that's another responsibility of DAG serialization, right? So as we discussed here, these are the three responsibilities. And what I'm going to be doing right now is I have a diagram which basically represents a lower level diagram of Airflow code base. And we're going to be seeing how those components actually address these responsibilities, right? Okay. So I think everyone must be familiar with Airflow scheduler command, right? Most of anyone who has used Airflow, they basically have two major components that they need to run. One is Airflow scheduler. The other one is Airflow web server. And now we also have triggers, but these two are still the main ones. So the DAG serialization starts as a part of Airflow scheduler process. So whenever you invoke an Airflow scheduler, you basically start another process, you invoke another class, which is called DAG file processor agent. Now this class basically starts a separate process, which is DAG file processor manager. So now these two are running as two different separate processes, right? And these two processes communicate to each other using OS pipes, right? And the kind of communication that happens is basically two different messages. One is agent signal, others are callbacks. So agent signals, you have three kind of agent signals: terminate manager, end manager, and then agent run once. I'll come to these type of signals, explain what they do in detail in a bit. But I think you must already be familiar with the callbacks. At least whosoever have used Airflow once, they must be familiar with the kind of callbacks you have. So you have two major callbacks. One is task level callbacks, another is DAG level callbacks, right? So task level callbacks is when you prepare your Airflow DAG, you specify different operators. So those, when goes to memory, they convert to a task, right? So operators equals to task there. Now they have two sort of callbacks, which is success callbacks and failure callbacks. So if the task succeeds, you can specify a certain logic that will get executed, and if it fails, you can specify the other logic. Same thing happens at the DAG level as well. There is also something called as SLAs, but I'll come to SLAs in a bit. So yeah, so at this point of time, we have two processes running. One is Airflow scheduler, another one is DAG file processor manager, right? And DAG file processor manager, basically as an input, it gets a DAG folder, right? What DAG folder we specify in Airflow configuration. Second is a second setting that it gets is whether this is an async mode or a sync mode. I'll come to that in a bit. So DAG folders used to basically have given at this point of time that, hey, Airflow, this is my folder where I have all my DAG files, right? And so DAG file processor works at this level, right? It has an infinite loop, which basically keeps looking at that particular folder, tries to generate DAG objects out of it. So there are multiple steps that happens along the way. So basically, so whenever this loop is getting created, you have a queue callback loop, in-memory object, which basically saves all the callbacks that you have passed here, right? So the callbacks has been triggered by scheduler. You basically save all those callbacks in an in-memory callback queue, and you keep that. This happens at different file levels. So basically, you say that, hey, my file is xyz.py, right, which contains a certain DAG. So you basically have a dictionary which just says that, hey, this is the file name and these are the callbacks that we saved there, right? So that's the first thing that happens. The second thing happens is basically it processes the agent signals. So if you look at the agent signals here, right? So you have terminate manager signal, you have end manager signal, and you have run agent one signal, right? So the first two signals is basically, as the name suggests, they basically Airflow scheduler ends certain process. So it just sends these signals as terminate manager or end manager. The difference between two is what the terminate manager signal basically sends a SIG term signal, which is Unix 15, and end manager basically sends a SIG kill signal, which is signal 9, I believe. And I think this is just sort of a forced version of stopping, DAG file processor, as this is a spawned process by scheduler. Agent run once is something that is related to async mode. I'll cover that in a bit, right? So at this point of time, we have covered first two steps here. One is queue callback, another one is process agent signals, right? So we have a queue at this point of time, which contains all the callbacks. And then the bit is to actually try to figure out try to go into every file that is there in the DAG folder, and just make sure that these files actually have a DAG within it, right? It can be any Python file or any file for that matter that can be within Airflow DAG folder, right? But you have to filter it out, right? So what would be an efficient way of doing that, right? So first thing first, you have a .airflow ignore file, which you can actually use to ignore certain files. If you are familiar with Git, you must be familiar with Git ignore file. So it is very similar to that. So basically you can specify that, hey, these are the files, even though they are Python files or XYZ files, don't consider them for the DAG parsing process. So you basically ignore all those files, right? Second thing is, yeah, so since DAG files are only created as a Python file, you basically have a Python extension to it. So that's the second level of filter that you have to figure out whether certain file contains a DAG or not. Now, this is an interesting functionality. So there is a zip file functionality. I actually didn't know that earlier looking at the code. So even if you have a tar file or a zip file within your DAG folder, it can actually unravel that, get the specific DAGs, and then use that DAGs for serialization, right? Okay, so at this point of time, what you have a Python file that we are a little sure of that will have a DAG object, probably have a DAG object. So the way to make sure is still, we have a heuristics here, right? So heuristics, anyone who's familiar with algorithm DS is basically sort of a, I won't call it a shortcut, but it's not an optimized way of doing something, right? There is no guaranteed of getting an optimized solution out of it. So we use a heuristics here, which basically simply looks for two strings within your DAG file. So it looks for a keyword called DAG and the second keyword called DAG. So if any of these keywords are there within your file content, that would be considered for parsing for DAG logic, right? Yeah. So the one more thing you can also sort file paths here. So if you look at this section here, so file path sort mode. So you have various options of sorting files. You can sort it based on when they were created, when they were modified. You have multiple options there as to control that part. So this is a part of Airflow's configuration. You can either use it using Airflow, specify Airflow configuration, or have a environment variable for that, right? So yeah, so at this point of time, yes, we have gone through all the files that are there in Airflow's DAG folder. Now, you have list of different file paths, right? And you have list of different callbacks that these things might have potential tags around within them, right? So what happens is, per file that you have encountered within the DAG folder, you basically run a different process per file, right? So for example, you have a file called, in Airflow home tags, you basically have snowflake.py. So that would actually be converted to a one single process. Now this process is solely responsible for monitoring that file, keeping it up to date, and processing all the callbacks, right? So as you can see here, so Airflow snowflake.py, and then you have callback request, and this is a separate process. And there is a separate entity within Airflow's code that handles that. That is DAG file processor process, right? And similarly, you have if you have 4 different files, it would create 4 different processes for each individual callback, each individual files. So now the input for this process is basically that, hey, you are this particular file, and these are the callback requests, right? So once you have that, there is the steps that is actually taken within this process itself. So you have DAG file processor process, and it spawns, actually there is a separation between 2 different classes here. One is the interface that is used by Airflow file processor manager, and it interacts with DAG file processor process, and it starts another entity, which is DAG file processor, right? So this basically, yeah. So I mean, you need to first, convert this Python file now at this point of time to a Python object, right? So the way we do it is we take that object and convert that to something called as DAG bag. Since one Python file can have multiple DAGs, right? So that's why it is called DAG bag, as to communicate it can have multiple DAGs. And now basically what you have is in-memory representation of a DAG, right? For a single file. Now we also process all the callbacks that you have earlier given, right? So we start running all the callbacks. This is just another list that you get, and you start processing these callbacks sequentially, right? So yeah, I mean, that's one of the things. And then you have serialization. That's the whole purpose of this whole flow. So you basically serialize these things into the tables that you can see on the right. So that's the serialization bit of it. And since we are doing this whole process from a DAC folder, a user can actually change a particular file as well, right? Or even delete it. Now, how that should affect the whole serialization process? The way it affects is basically either that will be updated in the database. So this whole flow needs to keep running in infinite loop so that it captures all the modifications or even deletions, right? So that's the whole flow. So this whole flow is actually keep running. This whole flow keeps running, and basically it just makes sure that the entire file. Is it mine? Okay, sorry. So this whole flow keeps on running and make sure that your DAC folder is up to date with what you have in the Airflow's database, right? And one more thing about the importing part, right? So I told that if there are some import errors, that needs to be represented and sent to users, right? So basically you have a table called import errors. So that table is actually getting populated in case there was a failure in creating a DAC bag out of a DAC file, right? So you populate all the import errors, and those errors are actually communicated to the end user in their web server, right? Airflow web server. So yeah, I think that's one part of it. Any questions anyone have? Okay. Yeah.
So once the files are serialized, stored in the database, let's say you need to execute on a Python on a Kubernetes execution.
Yeah.
So how the code that is serialized is being transported to the other pod to get executed.
So actually this is like kind of out of scope of this, because once you serialize it, then there is a scheduler scheduler loop that actually keeps on monitoring the tables that you have serialized with DAX, looks for the timetable data set, and based on that, it just starts execution of that. So this process, the serialization process, is only responsible for converting your DAC folders to something in your database, right? So yeah.
And how frequently, you said that loop that runs continuously.
Correct.
So the code which is running in the system can be out of date, and the file which is there in the file system might be.
Yeah, that's sometime that happens actually. So you usually either restart the scheduler or just wait for 5 seconds. Usually it's 5-second loops. So it just waits for 5 seconds, post that your file should be updated. That's the default. You can increase that behavior. There is something called as min file process interval. So you can set this. This is another configuration. There's another configuration in Airflow, and you can set this variable to reduce that time or increases based on your preference.
Thank you.
Any other questions?
So likewise, here are more than or like n number of processes continuously running. Okay, and assuming that there are files in GBs. Okay, so data will be processed one by one for during the serialization, and then go to the DB for them, right?
Yeah.
So how we will be managing like the process 1 executed, then process 2 executed, or like that, or the data which is stored in the DB is in the same way which we want in the file in.
Okay. Are you concerned about the scale of the
scaling,
how many files you have? Are you concerned about that? Yeah. So that precisely brings me to my next step in this. So basically what you have seen here is Airflow scheduler is invoking another process, which is, DAC file processor, right? So if you have that number of files, what you can do is you can have multiple DAC file processes running for you. So you can have different processes that will be a standalone DAC processor, a DAC file processor, and that will basically be monitoring. They can distribute load among themselves. So similar to high availability, you can have, you create parallel horizontal containers. So here you can create parallel processes to actually monitor that.
Like,
so that's okay.
Where all the configurations will be set. Like I want my whole records as a single file, as a single or row of entities in the database also. Okay, likewise, but in the parallel processing, like it will be consecutively like one record from file 1, second record from file 3, or like that, right?
Yeah. So basically, when you save a DAG, right? So this table actually contains file path as well. So the way you serialize it, it can be totally distributed among multiple processes, right? So you simply have a single, we just basically say that, hey, this is a DAG object, where it came from, when it was last parsed and stuff like that. So that whole thing has been stored in this table actually, which is called DAG.
Okay. But like this is not our final table, right?
This is sort of
not our final table in the database. Like we will be having some other simulation also for that.
So multiple processes will be populating to the same table.
Yeah.
So this is our final table. This is our interface. This is where the scheduler takes it from. So now if scheduler want to execute something, you basically have timetables, data sets, and various options where you can schedule or DAG. So it will be keep looking at, scheduler will keep looking at this table and then schedule the DAGs based on your cron job or timetables. Yeah.
Fair enough.
Any other questions? Yeah.
Okay. So when you say you're serializing the DAG, are you actually just serializing the task IDs, or like are you also, for example, serializing the involved Python function as well and somehow storing it in MySQL?
Yeah. So we used to pickle them. So if you have a Python operator, we pickle that object and then that's it. Yes. So basically you have a representation of task instances as well in memory.
And what about non-Python functions? Like,
sorry,
what about non-Python functions? If you want to run a Docker container from Airflow using Docker operator, like how are those kind of things serialized?
Sorry, I didn't get the question. Can you repeat?
What about non-Python functions?
Non-Python functions as in like didn't get...
like if you want to, for example, using the Docker operator, you want to just run a Docker container instead.
Separate operator is what you're saying. Yeah. So they also have, similar to how Python function is, they also have a representation in memory, right? So task instances are something that gets converted from operators to task instance, and they are basically the representation of operator within database. So they are same in a way. Yeah.
Okay. Thanks.
So earlier you mentioned there is a parameter to configure the sync actually here. So my question is related to the same. Is there a way of doing an on-demand basis also the sync?
Yes. Yeah. So you see this agent signal that's called agent run once. So you can request basically DAG file processor to go to the DAG folder, repeat this process.
How that request will go?
I can. So this is, I don't think that is exposed as of now. It is just used for async and sync mode, but I'll get back to you. I'm not sure how we can actually do that from command line or API.
Sure. Yeah. Thank you.
Yeah.
Hi. So once the DAG file processor processes the pipeline and then serializes it, so how do you handle the case for deletion when the file gets deleted? How is it cleaned up from the database?
So right now it's been marked as deleted to my best understanding. I'm not 100% sure about this, but I think it is marked for deletion. But if you logically think about it, you can simply delete that entry from the DAG table, right? So that can also be another option, but I can get back to you on that. I'm not entirely sure about which one of these two is implemented.
Okay.
Yeah.
Okay.
So you want to take this question?
Like even I am not very much sure because it's been like years I have seen that code. But what I remember vaguely is that this tables actually holds the DAG ID and the file path, and also timestamp like last refresh date, something like that, right? And it does not see that, okay, this DAG is not refreshed into like say a couple of hours or something like that. Then I think it is eligible for deletion or something like that, right? So that is my vague idea about it.
But yeah, we can confirm that and get back to you. Yeah. Two things to get back. Any other questions? Okay. I'll take that as a no, and moving forward. So this is just one flow of it, right? So this is where this is a process where we are actually invoking that file processor as part of Airflow scheduler, right? But you can also do it as a separate process. Now, why would you do that? Is basically if you have a lot of DAGs, a lot of files within your DAG folders, you can actually have a separate process, multiple separate process that can actually keep looking at your DAG folder and then serialize it accordingly, right? So there is also a diagram about that. So basically you see here, right? So if you have set Airflow scheduler standalone DAG processor as true, that basically means that, hey, I don't want to spawn a separate DAG processor for Airflow as part of scheduler. I want to spawn it as a different process. The way you do it is basically first you set this environment variable, right, to true, and then you run this command, which is Airflow DAG -processor, right? So this will spawn the same process for you as a separate DAG, as a separate process, and you can have multiple of these processes to actually keep up with the load, right? The only difference here is, since earlier we were spawning Airflow scheduler as Airflow scheduler was spawning another process, you could communicate between these processes with OS pipeline, but now you cannot do it since that's a separate process. So the way all callbacks are routed are basically using this table, which is callback request. So Airflow scheduler just populates, there is an interface, it just basically populates agent signals, agent callbacks within this table, and the DAG file processor manager is actually constantly looking at these this table to actually look for callbacks and agent signals. So that's another bit, right? So that's the only difference between these two instances. The other thing was, I spoke about agent run once, right? So this actually relates to the async mode. Now, why do we have async mode, right? So async mode is there for SQLite. When you are using SQLite as a database, as a metadatabase for Airflow, since SQLite is single-threaded, you can have multiple processes accessing the same SQLite database instance, right? So that's why you have async and sync mode. So this is a sync mode when you're using SQLite database. So what you do here is, so we want to basically ensure that either scheduler is accessing the database once, or it's the DAG file processor which is accessing both cannot access simultaneously, right? So the way we do it is basically we, if you're using actually SQLite database, you basically, it will actually automatically convert that into a sync mode. And what will happen then is, once you run Airflow scheduler, it will do its bit, and then it will create a agent signal, which is agent run once, and then share that. Sorry, I was referring to wrong diagram. My bad. So basically, Airflow scheduler will send that signal, which is which is agent run once, and this one signal, once we get the signal, then the DAG file processor actually checks for this signal and then processes forward. So that's how we basically handle sync and async mode here. Yeah, I think that's about it. Any questions? Okay. So yeah, also one small detail here. So you look at, I'll be sharing this diagram. So, if anyone wants to look at where this exactly happens in Airflow code base, what you can do is, I've marked all these instances with the reference number. You can actually go into this table, which basically contains the Airflow code base, where you can actually go and look at the code, what's happening down there, and hopefully understand it better. So yeah, thanks. That's I think that settles for everything. Thank you.
Okay, so we'll start with the second talk. Good evening, everyone. I'm Amok Desai from Cloudera, and I'll be presenting today on supercharging Airflow with custom Python packages. Let's begin. Yeah, small introduction about myself here. I'm. I'll just give a brief intro so that you people know me, and then you also know why I'm qualified enough to give this talk today. I work as a senior software engineer at Cloudera, and currently I'm working on something known as Cloudera Data Engineering. It's a tool that empowers data engineers to onboard Spark and Airflow operations at scale to an auto-scaling Kubernetes cluster. Apart from my day job, I've always been fascinated about open source, and I've always wanted to give time to it. And last year, I was I had the privilege of becoming a Apache Airflow committer. So I've been a committer for close to 6 months now, and my focus mainly revolves around Helm charts, the scheduler, the CNCF provider, Breeze, and documentation improvements. Apart from this, I've also been into the talks related to Airflow at local summits as well as few bigger ones. So I've done a couple of summits in Bangalore here in the last 1 year, and also talked about our no or low code approach to crafting DAGs at the Grand Airflow Summit that was held in Toronto last year. So one thing before we start, I would really like to extend my gratitude to a few supporting members here, because without whom I don't think I would be giving this talk today. So these are members both from dev and product side. From the dev and product, I would like to thank Vinod, Sunil, Sean, Philip, Tarun, Georgie, and Satya. And from our event side, we have Samriddhi, Suhas, and Mohammad Ansari, who was online. That's where we begin now. So before we actually jump into the solution, I would like us to focus a little bit on what the problem is, so that we can get to understand the solution better and can relate more to it. Speaking in terms of why we need custom Python packages, there are a couple of reasons for that. The first one being how does a normal user use Airflow, right? So they generally use the native libraries that Airflow provides, along with libraries that are available over public packages, and they construct their DAGs. So this is the general pattern. But sometimes there are a few advanced users or users bound by certain limitations that they need to use some sort of custom libraries that are not available in these public PyPy repos. By that, one example I can give is if a company maintains some sort of Python packages that they use natively. So that's one case where the users would want to construct their DAGs using such libraries. So this actually poses a serious challenge for users who want to run custom company code with their Airflow DAGs. So this actually needs to be solved because running this custom code, it's a basic need, and there's no direct way to do it when we deploy Airflow in a cloud-native fashion or on Kubernetes. If your deployment model is based out of Kubernetes or it's deployed in a cloud-native fashion, you would most likely face this challenge. Moving on, that does not mean that Airflow doesn't offer anything. So Airflow does have a few solutions for this, which have been working brilliantly in other deployment models. So a few of these which Airflow offers upstream are as follows. So the first one is if you write your custom code and package it as a module, and then you plan to add it to one of the folders that adds it to Airflow's Python path, then Airflow will be able to detect it, and you can construct your DAGs using your custom code. How you do this is by simply placing your custom code in directories that are part of Python path. And if you want to just reuse the existing directories that Airflow recognizes, you can go ahead with the DAGs or the plugins folders, and Airflow will be able to recognize these packages for you. The second one is if you want to do something a little more in a dynamic fashion, what you would do is you can add extra folders where you keep your code to Python path. So what we do here is we add an extra folder, and then we can use the well-known sys library in Python to load these packages at the DAG level. So it's as simple as doing something like sys.path.append in your DAG code, and the DAG will be able to use these modules. The last one is something that is a little more common. So you can package your code into the Python package and then install it with Airflow. So this basically is used for files that are not part of Python path. So generally what we do is we package it, we push it to a PyPy, and then we use pip to install it. and later we just import and use these packages in the DAGs. Now, coming to the challenges of these solutions on Kubernetes. So the first one, which was to add modules to one of these folders that Airflow detects through Python path, right? So one problem here is that the changes to both these DAGs and plugins are not reflected at runtime. And one question that remains unsolved is how will Airflow detect these changes in these code files? The second one, which was to add extra folders where you keep your code to Python path. Similar challenge again, how do we propagate these changes to all the Airflow pods, right? And the last one is slightly more tricky, which is packaging your code and then using pip to install. The problem here is if you are doing something along these lines, you need to install it in the Docker image of Airflow. And the problem with this is, again, you'll have to recompile your Docker image, and in cases post-deployment, you will have to again start updating and rolling out these updates. So one problem, the problem gets worse if you have a custom package which is in development. So that means that for every code change you make to this custom package, you will have to start building and rolling out updates for these Docker images. So the common theme we can observe across these problems is that in Kubernetes environment, the main reason these issues arise is because of the containerized nature of the pods. So we all know that Kubernetes containers are ephemeral and isolated, right? So in other words, manually installing these Python packages using pip or specifying the Python path won't work out because any changes that are made to a container's file system are not persistent, and they will obviously be lost when the container is either restarted or replaced. So ideally in such environments, the solution would be to package this custom code into Docker images and then deploy this image with Airflow. But the problem arises mainly here that we can do this during setup, but it's extremely impractical, and it's not worth it to do it repeatedly at a later stage. So yeah, we came up with a solution to these problems in form of something known as the custom global Python environment. So through this solution, the use cases which we are trying to handle, right, they look like this. So if I want to use a method that is belonging to one of my in-house packages, I want to use it in my Airflow tasks. That's one use case we're trying to fix. The second one is I want to use the method belonging to my in-house Python package, but at a DAG level. So at the top level of the DAG, which is available when the DAG is being passed by the scheduler. Coming to a very brief on the design aspect here, end of the day, it's a service that solves these earlier challenges. And so what it essentially does is it builds your global Python environment for Airflow. And this is mainly targeted for a post-deployment scenario. And what happens here is this service works in 3 steps. Very simply stating, the first one is, we need to create a definition for the environment that we are looking to deploy with Airflow. This generally happens in form of a pip repository definition. The second one is obviously to build the environment, which we defined earlier. And third one would be to activate the environment and use it along with Airflow. So let's dive slightly into the solution now. The first step, as I mentioned earlier, was creating the Python environment. So here we basically define the PyPy or the pip repository here. So generally speaking, I think the pip repository would need a few details from an end user, such as the PyPy URL, the credentials, and maybe certificates as well. So how we manage this in our system is that for the credentials portion, we use something known as CDE credentials. CDE stands for Cloudera Data Engineering here, which is where our Airflow is installed. So CDE credentials are nothing but it's a secure way to maintain and manage credentials within your CDE cluster. So what you can do is when you create a credential, it's securely stored as a Kubernetes secret. And it's mounted onto the builder job, also aka the service I was talking about earlier. In terms of then later part, which is in terms of the authentication, right? We rely on the PIP authentication itself, and there were a couple of options for the PIP authentication. So usually there are patterns such as the HTTP auth, the netrc, or the keyring. We went ahead with the netrc authentication here because it's easy to manage, one reason. The second one, it's a conf file, and it's fairly secure as well. And the main reason why we went for this was because there's no additional configuration needed at the PIP end for it to detect the netrc file. And in the end, you can also add certificates to the builder service. This is needed when your, let's say, your PyPy repository is SSL enabled, and you need to pass on certificates in order to connect to it. So these certificates can be added at the builder service definition, and this is essentially passed down as the cert flag to the pip command. So yeah, now that we have created the repository definition, what happens, right? How is it working? So we obviously need to use the repository definition from earlier, and we need to build out the VNV, or the virtual environment. So this is done by the internal builder service for us. So it runs the Python VNV command to create a VNV, and it runs the pip install command to the pip install command along with the requirements file you passed on to install the required libraries. So a thing to note here is that this VNV that is created will be stored in a target NFS that is already deployed in our Kubernetes cluster. So another thing that we are trying to manage is we only allow installation of the packages that are compliant to the constraints file of Airflow, so that we don't break the dependencies there. Yeah, so moving on. So yeah, when the resource builder service is installing, it's an asynchronous request, so we don't want to be entirely blank about it. So it's generally a good idea to gain some visibility into the process. So we expose an events API which provides these details about the installation progress that's going on. So it just has an array of JSON objects, and each of the elements here will tell you the main things that are important for us is the message and the timestamp, and we can also track it in terms of the user. So yeah, now that we have created the virtual environment, where do we store it, right? So in terms of storage, as I hinted about earlier, we will be storing these VNV packages on an NFS that is present in our Kubernetes cluster as a persistent volume claim. And at runtime, we will mount this onto the core pods, which is Airflow scheduler, the Airflow API server, and the workers as well. The Airflow API server is nothing but an API layer which we have built on top of Airflow to tailor some of our needs. So yeah, while starting up, we copy this environment from the NFS onto the local folders in these core pods. And we also mount a PVC that is used by our CRUD app that serves the workloads running against Cloudera data engineering. So that was end of the first part, where we created a pip repository, and we stopped there. Now, the second part, which I was mentioning earlier, was activation and using. So now that we have created it, how do we use it, right? So we need to make changes to the core pods here. So in that sense, we do things at the scheduler level as well as the worker level. So for the scheduler, we simply extend the entry point script, and we mount the relevant virtual environment, and then we activate it. So it's from the table, the code snippet below, you can see it's just a copy command followed by a source command to activate it. But you don't really have to activate it. You can also, it's also possible to use the Python interpreter in the VNV to run all the Python scripts from the VNV. For the workers, again, similar process. The pod mutation hook from the Kubernetes executor is used to use the environment variable and which is set in the Airflow scheduler, and it will generate the relevant mounts. The mounts are obviously put in as read-only, and we mount the persistent volume claims with a subpath feature to have some more control over placing it. For the activation portion, we do something slightly different, which is we directly source the VNV on the NFS instead of performing a copy, because this will avoid us the initial time penalty. Because in case of scheduler, it's just a single time operation, but there could be hundreds of tasks that are coming up. So we don't want that initial delay to be there. So the last step is to restart the services which you are interested in. So we perform restart for the Airflow scheduler and the Airflow API server, but we do not do it for the web server. So how we do this is using our CRUD app, which basically performs this deployment change. And once a deployment change is triggered, it will trigger a deployment restart, and hence the changes will take effect. So one important thing here is that in case this runs into error during activation, the environment is reset to the previous state, which was the working state, so that the system is still active. In terms of what value this brings across the table, it offers 4 things in particular. One is flexibility. So you can now basically execute your in-house or custom Python code within Airflow tasks for if you have specific data processing needs. Second one is extensibility. So what we are doing is we are complementing the built-in Airflow components, and we are allowing integration with specialized systems and services. Third one is integration. We can seamlessly integrate with external systems or APIs for an end-to-end data pipeline orchestration. And last one is control. Now that we have control over the custom code execution, when we try to target the performance, we can fine-tune it, and we can handle even specific business use cases. Before we jump into a demo, I would like to state the current status of operations that we are at right now. So you can add these custom Python packages for Airflow with CDE, and this is available both through UI as well as API. You can again perform 2 operations on it, which is updating these custom global environment and libraries, and you can also delete these custom global environment and libraries. So right now we are ready to ship it in the next release of CDE with both UI and API creation and activation being in scope. So I would like to jump into a live demo now. Bear with me because we know how live demos can be. I'll just share again. Okay, so I think, there we are. This is our the Cloudera data engineering console. So let's do one thing. Let's try to create a job first. And I'll try to create a job which is trying to use some sort of a package which Airflow does not already offer. So I have written a simple DAG here. Even before we go here, I would like to show you what this package actually does. It's a very weird package that I just discovered today morning. So it's a package known as inflect. So what this does is it generates plural, singular nouns, ordinals, etc., and it does some sort of string manipulation. So basically, I mean to say that if I can give a plural to it, it'll give me the singular version of it. So I tried to use this in my DAG here. So clearly this won't be there. The package won't be installed with Airflow. So I'm simply what I'm doing here is I'm simply initializing the engine, and then what I do is I just as I mentioned earlier, right? There's a method known as singular noun. So if you give it apples, it will give you apple, bananas, banana, etc. So I am just trying to do that, and then I'm returning it out here. And what I'm trying to do here is the DAG ID, right? I'm trying to generate the DAG ID through this function. So the DAG ID here is, I'm passing bananas, right? So in the end, it should be something like inflect plural to banana. So that's what I'm expecting, and that's not where I end. I also add three total tasks here. First and last ones are just dummy operators, but the one in the middle is a Python operator that is using the callable as the same singularized noun function, and I'm passing the same plural noun, which is bananas, to that particular function. So, and yeah, it's a linear lineage here. So let's try to run this by creating an Airflow job. So I'll just call this as inflect tag or something like, inflect tag. I will, let's try to upload it. So I have it right here. So I will upload the tag, create a new resource called maybe again inflect. Yeah, whatever. Do this, we upload it, and then let's try to create it, right? So as we expect, it should run into some sort of error. So yeah, what's the error? No module name, the inflect, which is expected. So now let me try activating the custom global environment. So I go here and I will try to activate it here. So we have a Airflow tab here through which you can activate it. So generally we are populating this particular index from PyPy as the default, because most packages that people generally use are from the PyPy simple index. So if let me just paste it here, and it's an index file, so it will get flooded. If I search for inflect, I'm just checking that it's there. Okay. There you go, right? Inflect is right here. Yeah, so we have the artifacts for inflect in this index. So I don't need to change the index. I'll just use this index. We don't need SSL certificates. We don't need username, password. So I'll just say validate. So once validated, on the top right, you can see completed. So now what we are interested in is the requirements file. So I've written a very simple requirement file, which is basically just having, I don't know if you can, let me zoom in a bit. Oops. Anyway, it's just having inflect inside. So I'm not specifying the version here, but I'll just let Airflow use based on its constraints. So let me upload this here as the requirement file that I'm interested in. This is the build process I was talking about earlier, where our internal service will pop up. It will take the requirements file. It will run two commands, right? Which is basically the pyenv creation, and that followed by the activation, and eventually it will put it on the NFS, as I mentioned earlier. So as it says, right, it will take a couple of minutes, but it's just one requirement, so I'm hoping it will be faster. So by end of this step, if you try to check into your NFS, you'll have this particular VNV created there. I'm just waiting for the UI to refresh so that we can proceed with the next step. Meanwhile, if you want, I can take a question up, and then we can do Q&A later as well. We'll just take one question till this happens. So if anyone has any question, we'll take one question now. It happened, but if anyone has a question, we can Sorry, can you repeat? Any performance impact on Airflow? No, there's no major performance impact because it's a one-time operation. It'll restart the pods and then the active environment is set to this one. It doesn't happen for every task out there. Okay, I'll proceed. I'll come back to Q&A. So yeah, once this is completed, you can see the libraries that it installed. It went with the 7.0.0, which I am assuming is the latest compatible one. So once this is done, what we get is we get to activate it. So the activate process is it's quite simple. It just restarts the restarts the core pods that we are interested in. So this shouldn't be too long. Yeah, there we go. It's done, right? So since this process is completed, we'll try with the same DAG again. But meanwhile, you can check a few operations here, update logs and delete in case something goes wrong. Now our current active environment is set to this one with inflect installed. So let's do one thing. Let's try the same exact same DAG from earlier. Yeah, I'm just having some short name. I'll just we don't have to upload it again because we uploaded earlier to that particular resource. So I'll just consume it and I'll create and run it now. So it shouldn't complain. Yeah, there we go. Okay, there's an error that, okay, it's paused. Okay, let me just unpause the schedule. So what have I defined? I have defined a schedule as, I believe, once. Yeah, it's once. So if unpausing should trigger it once. So I'll resume. So I'm going to the job runs. Yeah, this one, right? So we can see that it's started to execute. So we have a component known as submitter, which actually submits the DAG to Airflow. So we are just interested in the Airflow UI. So let's just go here and check. I also have it opened here as a separate tab. So we can also check from here. Yeah, here we have it, right? Oh, it's already success. But yeah, let's check what's happening. So yeah, I'll open the graph view. Yeah, there's the DAG, right? So yeah, first one and last one, they're not doing anything. So let's go to the Python operator and see if it printed that. Let me zoom in a bit. So yeah, I zoomed it in a bit. So yeah, we passed on bananas, right? So we got a banana there. So yeah, that's good. So it sort of worked as expected. So yeah, I'll just quickly go back to the presentation and wind up. Okay, it's not sharing. Sharing? Okay, it's sharing now. So yes. Okay, fine. So yeah, in terms of yeah, obviously no feature is perfect in the first go. So we also have some remaining work and future plans that we plan to address. So first one, which is a major challenge for us, is implementing the backup and restore for this custom Python environment so that users can seamlessly upgrade between versions of CD. And the other thing we have in mind is right now we're using a file share based approach, right? We're using NFS and other things which can be slow. So we are planning to move on from it into a more cloud native approach. So what we're thinking here is we will sort of pre-build the Docker images, the Docker runtime environment, and this will avoid us a major bottleneck from file share. And the other thing right now is that this feature is right now it's localized to only Python environments. We plan to extend it more than that. For instance, some of the operators require some dependencies to be in place. Like some might expect a class path to be somewhere, some might expect some binaries, etc. So we plan to basically extend a little more than the Python environments. So yeah, while solving this issue, we also ran into a lot of challenges, which the team tackled excellently. So yeah, the first one was keeping the system stable in any scenario out there. This is because system components like the Airflow scheduler are restarted. So if something goes wrong, the cluster could go in a very weird or unusable state. So we had to be very careful here. So this is something we solved using a concept known as CDE maintenance. I'll not dive into a lot of details, but it's a simple state machine based approach where we maintain a mirror image of the actual cluster and we perform operations of the active one. And there are two possibilities here, right? If something goes right or something goes wrong. So if something goes right, we wipe out the mirror image. But if something goes wrong, we wipe out the actual one and go ahead and use the mirror image. So it's inspired by the active-passive model. So this prevents system crash if these APIs are misused. And we also it also permits us to do a proper rollback in case of error states. The other challenge here is the in-place upgrades. This is not something that is entirely tackled. This is an ongoing effort and it will always be ongoing. That's because if there are changes in Python version or Airflow version, your custom library code could completely break. And the mitigation here would be to either update or rewrite the entire library based on the impact of the incident. So that was about the challenges. Yeah, so that was my time. Thank you everyone for taking out time to listen. So I can take a few questions and then we can move on to the next one.
So you said for the Python executive, the pods, which are the worker pods, and so there are two pods, the scheduler and the worker pods. So you said in the scheduler pod, we are mounting and then we are copying first and then we are activating.
Yes.
But for the worker pods, we are just mounting it to the place where it is supposed to be. So why don't we do the same thing in the scheduler?
In the scheduler, why don't we source it out? Yeah, that's what you're asking.
Like why go the activate process? Just mount it to the place where it is supposed to be.
No, why we are copying is it because if NFS gets corrupted, right? Scheduler is something we don't want to compromise. Workers are still something that can be spawned again.
Still, so there is another pod which is coming up, and there is one which was the original one. So if something goes on in the upcoming one, then we can just shut it down.
No, it sort of goes for a toss. The reason being the changes are made to the entry point and not at the pod level. It's made into the Docker image itself. So if something goes off, the scheduler, we don't want to lose the scheduler. We don't want to compromise it. Hence, we are making a copy of the virtual environment onto the scheduler's file system.
Okay. So we want to go back. That's
You have to go back in the whole process. We're trying to avoid that.
Thank you.
Any more questions?
Yeah, so definitely there is some time saving I can see there, right? But given that Airflow is used for batch data processing mostly, and maybe like to spin up the scheduler and a web server, and worker will of course come up eventually, right? It maybe take like 5 minutes roughly, because we used to do that, right? Like in 5 to 7 minutes, 8 minutes, it end-to-end process gets completed, right? Here we may be doing like 2 or 3 minutes. We are maybe saving some time, but the question is like, why we need to do and devise a totally new way while the whole industry is already doing and they stick to one way of doing the things and maybe not improvising so much things. And given that if I change anything into that, my Linux level, right, my container level, like some dependencies or something like that, I still need to build the images, the new images, and then I have to restart. Then I have to roll out those changes to the upstream, right? So just wanted to know like the real rationale behind why do we want to save a couple of minutes for a base system?
Okay, yeah, good question. It's not mainly about saving the time, right? That was not the motive behind designing this. The motive was mainly some of the users wanted the custom libraries that they were using, those were not mature. Those were already in development stage. So you can imagine, let's say the standard solution which the community everyone uses, right? Which is basically I make a code change, I bake the Docker image, so on and so forth. And now imagine that there are changes being made regularly to the custom library out there, right? So imagine the number of times you would have to bake the Docker image and do the whole process. And imagine if the custom library is being contributed by many more users at the same time. So that would make it even worse. So that was one of the reasons. And the second reason was the self-hosted PyPy, right? In that case also, they wanted everything to be in one sort of like a virtual domain, everything to be localized to it. So in those cases also, I think this would be hard baking it.
Well, I think for all the cloud providers, they do support custom PyPy, so I think that won't be the case. But yeah, I do see a point there. If you are actually developing a custom library and want to try it out right away with Airflow,
Yes,
that like maybe some new use case. But yeah,
it's not. I don't think it's a very traditional use case, that one, but it's a valid one because libraries are always being developed, and yeah, we want to keep up to speed, right? There's also the other solution, right? The Git sync container, but that doesn't go all the way till the scheduler. That can be used for the workers.
it is only for tag syncing.
That's only for tags, exactly. Yeah.
Hello. I had a question like, so let's say you have custom library being used in a pipeline already and someone upgrades it. So do you track like which pipeline DAG run essentially is using which version of that code? Because let's say if it fails later on and someone wants to know the root cause.
Yeah, very good question. I don't think we do that. We have the option to update the environment. So at one point, there is only one active global environment, but there is no like let's say audit, right? That's something you're hinting at. We don't have that as of now, where we maintain like which DAG used which version of which library. We don't have it right now.
Thank you.
So I'm imagining a scenario where you have deleted a library and added a library in the same Git commit, for example. So in that case, how do you ensure that the scheduler code and the scheduler restart, basically, how do you maintain this atomicity that, for example, if the restart happens first, then it won't be able to find the library and break. But if the deployment happens first, then it won't be able to find the new library. So
okay, yeah, again, very, very good question. So you're basically trying to tell that in my requirements file, let's say I had a library called A. And then I uploaded the requirements file, and later before building it, I deleted A, and then I created a new library with A again.
yes.
That's what you're trying to tell, right? The atomicity is it's maintained because we divide this into a 3-step process, right? So at any point, the second step, which is building the environment, at that point, whichever library is in an active state or whichever is referenced by the requirements file, that is the only one that is being built. So after the second step, if you update it, it'll take the older one. It will not take the new one. But if the old one is deleted entirely, that's a different question. It'll fail at the build step.
I see. Okay. Thank you.
Okay. So yeah, thank you.
Okay, guys, I hope you have energy for a small talk. And yeah, please sit down, get to your place, and we can start so that we all finish early and go home early. Okay, so I think I will start with a question that what is the maximum number of pipelines or DAGs you have seen running on a single Airflow cluster so far, like in your organization or at some customer, some friends, company, right? So what is that max number you have seen so far? Like any number, like 1,000, 100, 10,000 number of DAGs running out of a single Airflow instance, right? Because that is very crucial for what we are going to talk in next 10-20 slides, right? So just wanted to get that ballpark number. Any number is fine. I think Amok must know, right? Hundreds? Utkarsh? 6,000? 1,000? Nice. Okay, so let's take 6,000 as the highest number, okay? So just wanted to keep that number in mind. It's nothing to do it right now. Okay, cool. So let's proceed. Yeah. Okay, so here are two guys. The less smart is me. I'm Smith Maheshwari. I'm right now tech lead at Uber's data platform team and also PMC of Apache Airflow and some blah blah boring stuff. And I am here today with my smart colleague.
Maybe more like used to smart colleague. So I'm Rajat. I'm senior software in Uber Data Platform. Previously, I was part of Twitter's data platform team and Cisco. So, yeah, that's it.
Okay, so let's move on. Next slide. Yeah, so this is rough agenda. I think it's a simple, straightforward challenges, solution, how ecosystem evolved, and what are some future work. And of course, any questions you have in between, like you don't hold up, you can just shoot that question right there. Like don't wait for it. Yeah, next. Yeah, so I think let's go, little back in time. It was around like 2016, 17, right? And then at the time, Uber actually was running multiple orchestration solutions like, Airflow was one of them, of course, then Uzi, Jenkins, and some more custom solution made of Python, Closure, and, things like that, right? And they decided to unify all the workflows system and basically create a unified workflow solution. And after like doing a lot of research, and finally they settled onto Airflow. And at that time, Airflow 1.x, I think it was around Airflow 1.6 or 1.7 was available. So they settled onto Airflow basically, and then tried to run it on a scale. And then they found out, it was like it worked into various ways, good ways basically, like that expressivity, ease of use. You can extend Airflow easily. It can integrate with other systems easily, and there are so many good parts. So I don't want to focus like good parts, because that's why all we are here, because we have been using Airflow because of its good parts, right? But there are some places where it fell short, and just want to highlight those parts. The number one was the scale, right? So anybody who has used Airflow 1, can definitely know about it, right? Because I have used Airflow 1, and it was not scalable over few thousand pipelines. Does not matter how much compute you provide to it. Like it after a certain point, it won't scale, and then Uber's scale was way higher than that. So we'll come to that number later on. But it was not fitting the bill at the time. The code isolation, till very recently, till the DAG serialization happened, I think it was around 2020, roughly. Airflow services required the user written Python code to be available on all the services, and it will actually execute them on the scheduler, web server, worker, of course. And it was always a risk that a bad commit can ruin the whole system, can bring down the whole system. Then third one is like the APIs. So Airflow for a long time, did not have very stable APIs. They were experimental APIs, and they were like advertised itself like not meant for production uses, and it was actually lacking into many ways. And I think there are more some pointer like data aware scheduling. So of course, Airflow was really good at like cron based scheduling, But there is something like, the feature like data sets which has been evolved very recently, were not present actually at that time. And the security of the connections, there's another part of like all this things like data secret management, and those things actually happened after Airflow 2 or somewhere around that, right? So earlier it was not there. And also it is possible, I think that is possible today as well, that you can use the connections which are created by some other teams. If you are running a centralized Airflow environment, there is a possibility that you can, use some other connections from other teams into your decks, and maybe accidentally or, whatever, intentionally ruin the stuff, right? So I think those are the major parts. There would be some more, but we'll focus on to, I think, those ones only. Oh, okay. So now meet Piper. So Piper is basically, if you go by the definition, it is a data platform, a data workflow platform that allows user to author, automate and schedule data pipelines at scale. Also, it handles like things like failures, retries, alerting, and a lot of things which actually Airflow does, but some more extra things which Airflow do not offer, I think, right at the moment. Yeah. So we'll go a little like in the brief, the architectural view of Piper, and try to see like how it differ from Airflow, and we also go like how it got evolved at Uber, and then we'll talk about the other parts of it, right? But at the top, we have that different, I would say clients, the clients or like a starting point of it. So you can have the Python code, like the pipelines. User can write the pipelines, or they can use some third party, some other tools, like for example, Uwork. Uwork is a UI based workflow creation tool at Uber, or you can also use APIs. So we have APIs to create decks on the fly. So there are various other SDKs. There is a SDK available to author those decks using APIs. So eventually it will get converted into a serialized pipeline object, very similar to what Utkarsh actually explained in the first talk. So we have some services basically here which take this information and converts into serialized objects and put that into database. Then we have this tier, which is we call like scheduler tier. It has different components. We'll explain more in detail. But what it does, it is like the brain. I would call it just like Airflow scheduler. This also process the pipelines, identify when to schedule them, and basically assign the task, do the pool mapping, and eventually like send it out to the executor. And the third one, which is like executor tier, which is more or less very same, to what Airflow provides. We have different executors like Celery and then Kubernetes, executor as well, which eventually like take out the task, process it, and store its logs like into somewhere, and then put the database, update the database, and things like that. And then these are the third-party things where this task might be interacting with, like Presto, Hive. There are some more standard, like standard third-party systems what we have in Airflow. Next. Cool. So let's start with the evolution, basically, right? So sorry, yeah. No, actually, Piper is not open source. Yeah. So this is very initial. I would call a very initial version of Piper, which is very similar, exactly similar to like Airflow 1.x. It has basically a centralized database, web server, the scheduler is there, and then there are Celery workers running. The Python workflows are Python deck files, which basically processed by scheduler, and then there would be a Redis queue as well, which is not in the diagram. Pretty much like Airflow 1.x. Next. And I think by running the earlier version, we have encountered all such challenges which were listed into very first or second slide, right? And then to solve these challenges, Uber took a different route basically, and then all that earlier version, the earlier architecture, which actually does couple of interesting things, or like different things basically from Airflow. And here actually we kind of forked it out from Airflow, and though we are very much using the Airflow DSL, and then, like a lot of terminologies around like connections, variables, pipelines, everything actually matches with Airflow, but we still are a bit different. So the major difference was done at the scheduler level. So the first thing is that the scheduler was kind of discarded, and then we wrote like a new scheduler into Java, which was partition aware. It means that you can run n number of scheduler in parallel, and they can distribute work between themselves. And they are like independent. So if one scheduler fails, dies or something, the other scheduler will take up his work. So all this coordination was actually happening via this zookeeper service here. So that is the one major change, and the other major change is that the serializer basically. So we broke the Airflow scheduler, took out the serializer, and created a new service out of it. So what happens now? You write Python code, Python pipelines basically, and then the serializer would actually break that DAG, serialize in the very similar manner what Airflow does, and then put it into MySQL database, and then scheduler service. There are a couple of services actually would take out and start creating tasks basically from that. And it's still, this worker is still salary workers, which require the Python files for the execution. No change there. Sorry, I think there's so there's one thing I also forgot to name. This also we broke down the Airflow web server, and created a new service out of it. And as I mentioned, like the APIs which were very limited in Airflow, so we actually got a room to create lots of new APIs, which would actually required for our internal use cases. Cool. So that was the architecture one, and then this is very recent architecture, like I would say 2023 one. There's a small changes here. Like the first change is that we moved from Python based web server to Java based web server, and because of some internal things around authentication and authorization basically. So that is one thing. Another thing is that we also started using the multiple worker cluster. So what does it mean? That we are running a salary cluster, and our scheduler was actually pushing the task for that worker, but now we have different multiple clusters of salary running, and our scheduler actually can route the task to different salary cluster, as it's like as per the configuration of this pipeline and things like that. Some are very like high load pipelines and things like that, right? So we can actually make that logic and distribute it across. I think other services are remain more or less same. Of course, there are some more cleanups and things we added to clean up the database and keep it updated and things like that. So this is little deep dive onto that the scheduler process which I'm mentioning. Like it has contained actually 3 services. That box of scheduler contain the 3 services which are called orchestrator, scheduler, and prioritizer. So basically what is they do is, so the job of orchestrator is to talk to zookeeper and talk to the database, identify what is the distribution of pipelines, and then reassign the pipelines for the schedulers basically. So let's say there are 10 schedulers, 100 schedulers running. This guy would determine that which scheduler is going to pick up how many pipelines, or like workload assignment or reassignment is done by this service. Scheduler would be like still remain the brain. It would identify what is the task range, what is the next schedule, and things like that. And it will actually going to create new task instances. It's going to produce new task instances, and those actually get saved into the database as like task instance. And then the third service, which is another small service, which actually keep looking at the database, look at which are the task instances are recently got queued, or like I think there are logic around retries or whatever, right? And then this service actually put the task information into our centralized Redis instance basically. Or then this basically this there is a salary is running, right, which actually pick up from this Redis queue and finally going to execute it. The similar approach, if you want to send the information to say Kubernetes executors, like we can do very much from just making some changes into this service. Like so by breaking this whole thing, we are able to make changes into services, relatively fast, and we don't have to touch the other part. Like, these two parts we do not even need to touch if you want to use a new executor at all. I think these other things are like more or less same. I think we don't really not need to explain them again. Yeah. Right. Cool. Yeah. So I think this is what I talked in last 5-10 minutes, and this is like summary of this basically. So in 2016, a lot of different systems were in use, Uzi, Airflow, Jenkins, in-house, right? And then 2017, they decided to do unified workflow management platform and called it Piper. And then of course, the ecosystem got evolved. Like, Piper Core Pipelines is basically a repository where we, where we push all the pipelines created. Then it happened that 2018, the Piper V 1.1 evolved, where we actually broke down Airflow and, took out the good parts and modify maybe not so good parts into our own services, like schedulers, rewritten in Java, Zookeeper for HA. And then 2019, I think it's more around the security of data warehouses, which we have. We have actually 2 data warehouses, primary and secondary, around that one. We launch also the API-based pipelines, which is basically called managed pipelines, where you just post a JSON blob, and it will get converted into a pipeline. It will be actually treated as a regular pipeline afterwards. So you don't need to write any Python code for that, right? Then we have like some other hosted environment, like for dev, for development, you can use the Uber, like a pod-based sandbox environment. Or we have something called user staging, which is basically end-to-end testing environment. So in Uber, we have like, we have centralized environments. So we do not have hundreds of environments are running for Piper. So there is a one production instance of Piper, and that is a single instance, which is actually running all the pipelines for everybody. Then there's the UWork what launch. UWork is basically UI-based pipeline authoring tool. It is, I think it's out of the box workflows. Basically, you just drag and drop and create pipelines. And then I think in the recent years, like some more things about like multiple executors, scaling out the organizer, using moving to Python 3, which was something pending from quite some time. So all those things were done. And also recent time, we have a very focus into this disaster recovery, which is not, out of the box thing from Airflow, right? How you actually running two systems in parallel in 2 different data centers, and then how you do disaster recovery from, one to another one. And also in the ecosystem, we got evolved around the governance, like we maintain all the tiering, lineage, letting, and things like that. And we also recently moved to Piper monorepo, which is basically Python monorepo. In Uber earlier, it was all the micro repos across, across Uber. Cool. So I think this is the number. So don't want to go through all the numbers, but the major one is like we have around 200K active pipelines running from one Piper instance or one Piper cluster, right? And then we are roughly doing 750K, like a 3/4 of a million task execution per day. And we are running right now with 1,000 node Celery executors clusters, basically. So every cluster is like eight slots, right? 8 slots per Celery node. So we are running at a capacity of 8,000 parallel task execution. I think in this 1 minute is basically average task scheduling delay, which is quite good if you compare with the Airflow 1.x numbers. Like maybe it's not very high compared to Airflow 2, but compared to Airflow 1 I think is quite good. This is another interesting one. We are getting roughly more than 100 commits every day into this Piper Core Pipelines, which is basically a place where you write pipelines. So every day we get more than 100 commits into a single repository. Like people are adding pipelines or modifying pipelines or deleting pipelines from that repository, like from that folder, right? So that is also an interesting number. Yeah, I think that's it. And Rajat will talk about ecosystem.
Thank you, Sumit.
Question.
Yeah, sorry to come at this late, but I did see that you're using Zookeeper here, right?
Yeah.
What exactly are you? Is it for workers or for?
No. Workers don't need Zookeeper, right? Zookeeper is required for multiple things, right? One is that the leader election. So, for example, in this organizer is not here, right? Yeah. So basically, there's a leader. It's in, is it right?
I think it's the previous one.
Yeah, serializer, right? Yeah. I'm sorry. Yeah. So this is for a couple of things. One is for the leader election. So between the serializer, right? So earlier the design was So like one of the machine basically would act as a leader and would process the pipeline. So to determine who is the leader. So that is what Zookeeper is used, and the another one is that for this person, like the scheduler one. Next slide. Here, right? So what we do is basically this orchestrator do a mapping of all the pipelines in the database and look at all the nodes, like how many nodes are in the system. Like they said, there are 20 schedulers are running, right? Then it will do a mapping. Okay, so it will assign roughly 10,000 pipelines. Let's say 10,000 pipelines per scheduler, and put it back into the Zookeeper. Okay, so when this node will come up, it knows which pipeline I need to look up. It will go and look at in the Zookeeper. Okay, give me the list of my pipelines, and I will process on those ones only. Right. So this is another use case for Zookeeper. So like leader election and the assignments of pipelines.
So you were able to integrate it because you have a custom scheduler and this thing, right? Custom, I think, whatever that component was.
Yeah,
prioritized.
call it like custom scheduler because it has, of course, it got forked out from Airflow and rewritten to Java.
Okay.
So we could actually add our own logic.
So why specifically Airflow? Because I think Uzi already has many of these capabilities, right? Correct me if I'm wrong.
Yeah, so of course Uzi might have it, but I think that what lacks mainly in Uzi, and I'm not speaking for myself because I'm speaking somebody like who took the decision in 2016. But what I can sense or easily that Uzi did not have that expressivity, right? You cannot express the things. It's like all XML based ones, and we think that people would not be able to write 2,200K pipelines on Uzi. Like it's not that easy. That our use case would not actually evolve. We required a good DSL or actually language-based DSL, which can be incorporated by and adopted by our user community, like the people who are going to use this system. So probably that was the reason why using.
Mainly looks like it was ease of use plus non-big data.
Yeah, exactly right. Yeah.
Okay.
Lot of like so many good things of Airflow. That is why we actually chose to go with Airflow.
Thank you.
Thank you. So I'll be talking about Piper ecosystem, which is essentially a combination of infrastructure and application components that constitute Uber's data workflow platform management system. Yeah, so the first component is Piper UI. This is being deprecated, but still widely used. So this is the web server. So UI for the Piper. If you see, it's more or less like Airflow because it's derived from Airflow. We have added or modified some components. So there's like graph view, this is tree view, and if you click on any task instance, it's almost the same as Airflow. We have added something like lineage and on that is Uber specific. Next slide. Now Piper UI is being deprecated in favor of UWork. UWork stands for Unified Workflow Orchestration. This is another centralized dashboard in Uber for batch work jobs and streaming workloads. So this is a powerful tool. So Piper UI essentially gave you the monitoring aspect of workflows where you can execute maybe workflow and monitor its run, right? This is actually like it gives you a ability to create workflows on the fly. So you can have like a drag and drop feature. For example, this is a sample pipeline, and here are the different tasks that we have. Let's say Bash or Hive task or Spark tasks. You can simply drag and drop and connect those components to create any workflow. This has its limitations, like some complex workflows might not be possible, but most of the majority use cases gets covered by it. So this is one of the cool features of UWork, which I really liked. You can directly create your workflow here, test it out, and deploy it in production. So it provides you like a code-free way to create workflows at Uber. Okay, so Sumit mentioned pipelines creation via API, right? So we have two pipeline types essentially at Uber. One is the SDK one, which is more or less Python code-based pipelines that you must be familiar, like DAGs that you create in Python. So they provide complex functionalities which you can implement and extend existing tasks or actions. So actions at Piper is, you can think of it same as you use hooks in Airflow. So they provide integration with many sources as well as you can extend them. So managed pipeline is JSON-based pipelines which are created via REST APIs. So this is an example of a managed pipeline payload which you can pass to the API to create a pipeline. So this is just a simple my pipeline which has one task, which is Hive task, and it has its query. So this is useful where like we had some use cases where the services are generating pipelines, multiple pipelines, and the generation is dependent on external configurations coming from external services. So if we have pipeline drivers for SDK pipelines and like and managed pipelines. So if we had moved it into Piper core, so that will actually complicate it out, and like it will be dependent on external services, APIs, and failures, right? So we gave this ability for other services, which can, generate those configurations, get those configurations, and create these managed pipelines. And we don't need to serialize it on anything, right? It's already serialized. So it directly gets stored into a database and directly is visible like almost instantly in UI. Okay, yeah. So since I think most are Airflow users, so you are all aware of time-based scheduling, right? That's cron-based, where pipeline gets scheduled every hour or every day. Most of like in data platform, we are more heavy on the use case for data-aware scheduling. So this is enhancing the scheduling flexibility from run only the time-based to a trigger-based scheduling, where the trigger conditions can be data freshness, where it's like how updated is your data, or data completeness, how complete is your data, is it lacking information or not, and pipeline execution history, let's say like when was your last pipeline completed. So this is more like a service, sidecar service, which we have. So how you create this kind of schedule, you create a YAML config out of here, for example, this. So, and it has a pipeline ID, the destination table, it mostly a Hive tables, which can on which you want data freshness or data completeness checks. And last task defines the last task of the pipeline, which you are adding. We need it for determining the pipeline execution history. So here is get the most latent source table updated. If it's updated in the last execution time, and seconds is last execution and is 14400 seconds, and it's not running currently. So this constitutes our rule, and once this rule is met, your pipeline gets triggered. So it's more of a trigger-based scheduling, which is useful for if you have data sets on which your pipeline is dependent on. Yeah, so Piper user staging is a dedicated environment for users to test out their pipeline. So it's based on a multi-tenant model. So we only have a single Piper user staging environment on which like almost very large number, like thousands of users create their pipeline. So what they use is a dev branch for their pipeline. So we can have 10 users creating a pipeline with same ID with different dev branches. So we have a CLI based model here for deployment. So we have a Piper dev CLI. Or when a user wants, they have a dev at Uber, like all the users, mostly developers, have a dev pod, and in there the Piper dev CLI comes inbuilt. And once let's say they want to deploy a pipeline, they will run a Piper dev deploy command with their pipeline ID, with the dev branch as well as the path to the pipeline. So once that is done, internally, like we create a session and develop deployment for them, deployment ID and session ID, and we may map those to the pipeline they're creating. We also create the pipeline ID dynamically to support this, because we do not want pipeline ID conflicts between users. So we append the session ID, which is based on the dev branch that they're using. So we can have and then the pipeline code is downloaded and uploaded to TerraBlob, and then it is fetched into the workers directly. We do have some kind of restriction on the pipeline scheduling to prevent misuse, because this is a testing cluster intended for only pipeline testing. So we have this restriction where only one pipeline execution would be done per deployment. So if you want to test a pipeline, you deploy it once, it will be run once, and you can see your result, and that's it. We do have some allow listing for special use cases, but mostly it's restricted to one pipeline run per deployment. Yeah, next. So this is the design architecture for user staging. So we have a user dev pod, which is a container-based dev pod, which already contains Piper devs CLI. Once you, let's say, do a Piper dev deploy command, it will fire a create deployment request to the UI Piper web, and then it will essentially create a Piper organize, or the serialization command. It will queue it to the Redis queue. We have two partitions in the executor side, so they are listing two different queues. So that when one is Piper dev deployment partition, which will be listening to the queued deployments, and once those deployments are taken there, it will fetch the dev branch from the Git repository, and it will validate the deployment. If it's correct, let's say it might have import error, so it will throw it back. It will update the database, MySQL database, with those results if it contained error or not. And it Piper dev also fires a get deployment on regular intervals while the command is running to fetch the deployment status. So that way it would get it. If it's, let's say, successful, then it will serialize the pipeline and store it into a MySQL database. Also, it will push the dev branch to a TerraBlob store. And so we already have graph runner services, which Sumit explained. So we have scheduler, which will be polling this MySQL metadata database for any ready to be scheduled task. And if it finds those, it will be pushing those to a Redis queue. That will be a different queue, and which will be polled by the compute partitions that we have in executor services, and they will be launching the task. So when we serialize, we actually, to have those restrictions, we mutate the start and end dates and for those pipelines so that they are only executed once. Yeah, so the multi-executor environment, this is what we have been talking about. So this is essentially, we segregate the celery clusters based on partitions. So for example, we had a use case. Since you are working on celery executors, we all, I think, might be knowing these limitations. There's no runtime isolation, right? One worker process can actually consume all the memory and maybe shut down the host and impacting other jobs. So these all things, to avoid this, we had a different partition. So we, for critical jobs, we provide a dedicated environment, for example. So for example, like GDW is a team at Uber, which mostly owns high tier pipelines. I'll explain what's high tier, but it's mostly like critical jobs. So we provided a separate dedicated salary cluster there as a service. And like when graph runner services like scheduler is pushing the task or prioritizer, so when scheduler creates the task instances for this pipeline, it will check if the pipeline is belonging to any of the known partition IDs. And once it's known, it will push the task into a separate Redis queue. It won't put it to the default queue, which go into a general Piper executors, but it will go into somewhat dedicated queues, which are used for, like let's say GDW will have its own queue. So it will be polling that task. So currently we like mostly for now support only salary executors, but like it is kind of extensible. Like we can move on to support Kubernetes executors. Let's say we want some jobs to be run only on Kubernetes pods, so we can support both type of executor types. But currently it's majority use cases salary here. Yeah. Workflow governance. So this is Uber's answer to standardize and safeguard workflows by promoting accountability as well as delineating the jobs into like critical or non-critical. So we have so many pipelines. We need to know what are critical ones, which one we can prioritize to, like if you want to save something, we will save those first. So we have tier-wise segregation of workflows where like tier 1 to tier 5, tier 1 being the highest priority. So those are tier 1 and tier 2 are the most critical workflows. And like these are automatically classified on the basis of the data sets that they use. So let's say if they are working on a critical Hive data set, it's already tier 1. So the pipeline will automatically be classified as tier 1. So workflow governance is essentially to standardize the workflows being used at Uber and like ensure that they have reliability. So let's say if you have tier 1 or tier 2 pipeline, we do not want it to fail and we want to ensure that it works fine. So we have restrictions like alerting policies and enforce ownership. So they have certain alerts on them which you cannot turn off. They will automatically be set up when you create a tier 1 pipeline or tier 2 pipeline. And there must be clear accountability for that pipeline. Like it must have an owner and you own asset assigned to it. So like the team who's owning that pipeline. It also promotes cost efficiency. So like tier 5, like for example, tier 4 and tier 5, we assume them to be more of a testing pipelines. So we automatically have an expiry date set up. That's what we call retention, like for 1 month for tier 5 and 1 year for tier 4. So that like we automatically shut down any unused pipelines in the future. You do get an alert before its expiry so that you can renew it. Resource management policies also apply in workflow governance, where let's say like let's say high tier jobs, they can get access to high tier resources and more concurrency than lower tier ones. So that way we try to avoid unnecessary cost by low tier pipelines. Next. So secret management in Piper is done by Uber's secret management service. This is a service which is used to manage confidential data securely and distribute it across Uber. So this provides out-of-the-box functionalities for us like auditing, access controls, as well as automatic rotation of secrets or keys. So if you want to use it in pipelines, so how it works, like it comes like as a dictionary in our config. So you can just do a config.get and then your secret key name and get those credentials. We do have like when they're mounted on the containers, so when they're mounted on the containers, they are given specific ownership permissions so that they are not misused by any other pipeline. Yes.
So this pipeline secret management is something internal to Uber, right?
Yeah.
Why not use HashiCorp Vault, for example? I mean, even it supports APIs, Vault also. I mean, is something wrong with Vault? Is there a shortcoming on Vault? Why you're not using that?
Essentially, because we already have a use secret service by Uber, which is like conforming to the standards which Uber wants, right? And we already have integrations with different services based on this use secret or the Uber's management.
So is it older than Vault? I mean, Vault has been there for a long time, many years now. You could have used that instead of writing your own service.
True, but like in security, you will find like we do not have to worry about it, right? If we are going to use some third party, then we need to ensure that it's updated and all. But it's not like data platforms, like our team's job. Then like if we can delineate it to something like Uber security team, and they maintain, so like security standards at Uber are, I think they're pretty good.
You do realize that if you expose your secret management to internet, it may also get hacked very immediately.
Sorry, so just to add to the previous point that about the secret service versus the Vault or other services, right? So this is first thing, right? Uber works into the centralized model, right? So like for example, Piper team is responsible for taking decisions for workflow management solutions, right? And then we take those decisions, they are like scrutinized up to a lot. It's not that we just take those decisions out of the box, right? But yeah, once we take the decisions, like all the other people, all the other teams who are using it, they have to adhere to it, like what you've taken. So similarly, we do not know the internals, why then there's a service, why it is different, or whether it's the same like some of the vaults out there, right? It might be just a improvised version of those services. But for us, it's called a secret management service at Uber, right? And we have to use it, like, apart from like putting on internet, and I think those things probably not valid. And those things must have been taken care of, because at Uber, the security, like the utmost thing. And just for example, in Airflow, we can use secret managers, right? Like Vault or Google or Amazon. But what I last known is that I can still access to a secret in one of my deck, and I might not have access to the secret, right? But in Uber, that is not possible. So let's say if you are using a secret from your pipeline, for example, in this case, like config.get this secret name, right? Your deck won't be able to get it, like if you do not have access to that secret. So up to that level of secret management is already inbuilt in the tooling. So forget about the out of the Uber. Even within the Uber, we do not have access to secrets of other people. Actually, it
makes sense. Yeah.
Yeah, if you can hack with this much information, you're pretty good. Okay. Now. Okay, so one of the primary use cases where we had to make our own Piper instead of Airflow or any other open source because of disaster recovery scenarios, which is one of the critical requirements at Uber. So this is mostly like we have two zones here, Phoenix and DCA, where Phoenix is mostly our primary data center. And like the disaster recovery is essentially like if its Phoenix goes down, we want at least the critical jobs to run on the secondary data center. At the same time, we do not want to spend so much cost on like compute, which is like not being used mostly on DCA. So how do we save computing is like whenever a pipeline, let's say, is running and it's generating data sets, we store all those data sets, we replicate those into the secondary data center as well, which we call HiveSync. And the compute, we only keep necessary compute, which is like required, which can run all the tier 1 and tier 2 pipelines. So that's where, again, tier-based prioritization comes in handy for us, that we know already what are critical jobs and which we need to ensure that they run. So we keep some reserve capacity already into the secondary, as well as send some resources for tier 3 plus. And next. So yeah, so let's say a disaster happens and the primary goes down, right? So what will happen? So essentially, like we have Piper Phoenix 2, which is our primary data center, is doing some we have data sets in HDFS. So we hit a pause there. Like in general cases, DCA is not running. Already replication is happening in the backend in normal cases. Once failure happens, the Phoenix is paused and DCA is running, and we already have Hive sync, and we do have to do a reverse Hive sync, which is like reverse replication to Phoenix when it comes up. So like how we pause it. So we have like an admin pause functionality where all pipelines get paused on Phoenix, and tier 1 and tier 2 pipelines are migrated to DCA and they are unpaused there. So once they unpause, they start running and they start executing the data set. There's a lot more functionality which happens in backend, which I'm not going to explain because might be out of scope and too much to absorb. But essentially, like we pause all the pipelines in Phoenix, we switch them on in DCA, and they start producing data sets, which then again get replicated back to Phoenix. Let's say once it recovers, we have a rewind case where we actually, whenever we do failover, we have a global checkpoint saved in our database, like till from when the failover started. So for tier 3 plus, we actually rewind them and they start back from that same point. So they kind of do a backfill, but they can also avoid this by ensuring like there's a parameter for that as well, like auto backfill. So even I think tier 1, tier 2 pipelines are also rewinded to some extent because this replication has some lag and it might not be complete, right? It might not have, due to the pause and it might have failed and there might be incomplete data sets. So yeah, that's much for disaster recovery. Yeah, for future work in Piper, we have Kubernetes executors which are coming up mostly because Celery's support is kind of limited at Uber, and we are moving away from Python-based systems to Java-based. We want to move away. And runtime isolation is what I told, like it's not provided in Celery executor, so that will be met by Kubernetes executors. We also want to provide end-to-end pipeline testing. So we already have user staging environment, right? But it does take some time, let's say 10 minutes to 5 to 10 minutes to deploy a pipe, and then you have to test for, let's say, Hive job or Spark, Hive query or Spark job. We want to provide this in the containerized dev pod, which we already have. So instead of having all those Uber Piper system, user staging system, you just run the CLI and it will run your pipeline there itself locally. So we are exploring those cases as well. Sumit, you want to take the further ones?
Yeah, I think when I say future work, it is very specific to, something which is already available in Airflow and we want to take it out. And there are something which we maybe not able to share right now because it is more of like internal to us as of now. So this orange is basically something which we want to do right now or already working on. And this blue is basically, it's good to have, and we are looking at Airflow and we're looking Airflow as a source of inspiration and things we want to actually incorporate into our system, right? So things like, deferred task for the cost saving, right? Especially when we move to Kubernetes executors, that would be even actually more important. Like dynamic task is another important concept and we liked it. And then of course there's improved DSL, like the task group and the task, and I think there are more, like there are plenty of them actually, right? So maybe some of them we want to actually have it in our system, but it's not burning, and we may want to use it depending upon the resources. Yeah. Sorry, your voice is not.
Right. Thanks for wonderful talk. I want to ask what kind of monitoring and observability you are using for your multiple executor schedulers?
Actually, we have a very detailed monitoring and observability systems into place, which we have not covered into any of slides here. But actually, all of our code actually keep on emitting matrices, be it the scheduler be it the worker level or be it at the other like the serializer level, right? And overall, we have like various dashboards, and we actually omit more than 100 matrices to keep monitoring those things. So all these numbers about like the task latencies and the things like that, the scheduler loop time, everything we get it from the dashboards only. And we kind of review those dashboards as very regular interval, like every week, and try to find out if there is any deep into any numbers or things like that. Yeah.
Since these services are automatically orchestrated, it's like pull or push based. Like it's kind of agent when the services are coming up that gets inbuilt as the orchestration is happening.
Sorry, you mean to say the services like Piper services when they come up? What kind of agent?
I mean, the container services which you're talking about,
Yeah.
the scheduler services. So basically, at that point in time when VM or containers are coming up, the agent is sitting inside it as the services is spinning.
Agent for sending the matrices?
Yes.
Yeah, exactly right. So as of now, we are into like both worlds. We are into on-premises as well, using Apache Mesos containers, and then moving into like Kubernetes one as well, right? And then these agents are basically part of the bundle itself, basically, which get deployed to the system. And then everything, as I mentioned earlier, we have like centralized service for everything. So we have a Grafana-based observability system, which we can just rely on that, okay, it will going to work. It's black box for us. We just emit the matrices, and then consume those matrices into this Grafana dashboards.
Yeah. Hi. One question. When you were talking about the failover thing, disaster recovery, you said the tier 3 and tier 4 gets burst into the cloud. Am I right?
Yeah.
So when you burst into the cloud, you also have to move a lot of data into the cloud. Am I right? For the DAGs to work on them?
Okay.
How do you move? I mean, am I right, or is there something else about it?
So we pause those pipelines. We do not run those during disaster recovery.
So you don't burst into cloud?
No.
Okay, your slide said you bursted into cloud. A slide previous than this, where you were explaining this one, I think somewhere it was written burst into cloud. Yeah, the point over there, burst into cloud on demand for tier 3 workloads.
Actually, that is true. Given that this data center do not have the compute, right? And we have only a small compute for tier 1 and tier 2. But let's say this outage is going long, let's say some reason, right? Like maybe 5 or 7 days, right? Then
that is fine.
Yeah,
I agree that I understood that part. My question is that when you burst into cloud,
correct,
the data, tier 3 data and tier 4 data, that also has to be moved to the cloud, right?
Exactly. That's true. So there is a something which is ongoing, and we did not have those details here. Like we did not edit those details specifically here. But that is also there. Like, this syncing is actually not only to DC, like 2 DCs. It is also happening to cloud as well, but not all the data sets. Like some of the data set are being synced to cloud as well. And when this thing happen, those data set will get actually produced into the cloud, and basically get reverse synced into that DCs.
But wouldn't moving into cloud in real time, I mean, it can't be real time. It will take a lot of time.
Yes.
Is that acceptable to you?
Yes. So that's why we are moving only at tier 3 and above data, and then our SLA for such tiers is like 3 to 5 days basically.
Okay.
So it is not 1 hour, 2 hours. We're saying within 1 hour we can actually move all the tier 1, tier 2 pipelines to the new DC, like the failover DC. But for tier 3, 4, 5, it may take up to 3 days, and that it is acceptable because the data sets does not need to be that refreshed. This is like most say some analytics I want to do from past year data. It does not need to be like very, very refreshed. I can live with that, like 3 days old data as well, right?
Got it.
Those things, yeah.
And Uber must be having a lot of data centers across the world, right?
No, I think we have only like 2 data centers. Like I think you see there are 2 different things, right? The one is we are talking about the data side of thing, and there could be that different like services side of thing, right? So I'm not very sure about how the Uber services operate. Basically, what are data centers they have? I don't know. Like maybe they have India, China, everywhere. Like not China, India and US or Europe, everywhere, right? But for data, if you talk about the data side, I think we have only 2 data centers.
Okay. The reason I asked that was that assuming you had multiple DCs, probably each DC would have its own setup of Piper and Airflow setup, right?
Right.
So you are only computing localized data.
Yeah, that is true. But we do not plan to have multiple DCs. We have planned only 2 DCs. Basically, one is the main one is the failover. That's it.
Okay.
Like we do not plan to have like multiple DCs, right? So
All right.
otherwise, this problem will actually keep on increasing manifold, right? Like you have the 4 DCs, then of course, then it will become 4 sinks and all those things will start happening, right? So, but we do not have any plan or any like anything.
Thank you.
DC one, right?
So you talked about data freshness based triggers.
Yeah.
Like, can you share how they are different from Airflow sensors, or are they the same, or like how do they work? Like a little bit about the implementation as well.
Yeah, good question. So yeah, we achieve that in Airflow by using sensors. Like we have some sensors which mostly pull or do a select some query over the tables, right, which we want and then execute. So essentially the difference here lies in like that takes up one of your pool slots, right? First of all, like that sensor will be checking that pipeline, the table. If it's not there, it will reschedule itself, or maybe it will like now it reschedules. Here it will be, it's handled by that service itself. So what we have is there's a separate process running, jumpstart, which we call, and for like let's say per team we have a process, and it essentially like it runs every minute or 5 minutes, and like it is checking for entire pipelines in one go. So like let's say one team has 100 pipeline, it will do a check on all those 100 pipelines in one single check. So yeah, that's the difference. That there's that's the difference mostly.
So there's an inherent assumption here that these 100 pipelines would be very fast to check, right? Otherwise, that would affect your scheduler delay.
Yeah. So like we have the signals are mostly, we have regulated them. Like you cannot have your custom signal. It's mostly like fixed, which we use kind of a Ginger templating style.
Thanks. Makes sense.
Hi. I heard you mention that in your future tasks that you're migrating from Python to Java. So does that anything to do with the better operability of these tools?
Sorry, what operator? Like last point?
I mean, you mentioned that in future tasks, like you were planning to move from Python to Java. So does that have anything to do with the way you operate or the performance, improvisation, anything?
It's a mix of both. So at Uber, Java is more supported, like in general. So we have a lot more integrations with Java, which comes from lower level platform.
Understood.
Also, the Python, like we have Celery. So we have a issue with Celery as well, because currently the Celery supports only a single Redis instance.
Okay.
So our main bottleneck actually lies in Celery Redis instance, because a single Redis instance can only handle up to 10,000 connections. So let's say we can only have, if we have 1,000 executors already, right? So they have 8 processes. So 8,000 connections, we get it from there itself. So it essentially forms a bottleneck. So we want to move away from Celery. And one way is to upgrade Celery version to, because, and then it works on, I think, AMQP protocol, right? And which is not supported on Celery or on Redis side. That's what I know, I think. So on the Redis cluster side. So we want to move away from Celery, as well as like from the API side, why we are moving from Python to Java is mostly because of integrations which comes from like Java team here. Like we do not have a dedicated Python team. I think it's been set up now. But like we have like authentication, authorization, context, integrations, all those things directly coming from the libraries that they have.
Actually, my point was that whether choosing to use either Python or Java, will that have any impact in scalability or performance, anything? Is that a reason why you guys are moving from Python to Java?
So I think there is a miscommunication. I think we do not want to move everything into Java. Maybe some of the services, for example, the API service which we wrote in Python, it does not have the support, like internal support for authorization and authentication by like as a centralized team. Let's say, as I told, everything is centralized, right? So we do not want to redo the work, right? So somebody is supporting already, then they said, okay, we do not support in Python and that is supported in Java. So let's switch the service into Java, something like that, right? So that is the intention basically, that we do not want to switch everything right now. The only thing is that which is not supported by a certain team, maybe we can use something which is supported already, right? So that is one reason. The second reason about the performance, those things, I think that is at the current level, I don't think that is in line to our thought process as of now, because whatever services they are using, even they are Python based, right? They are working just fine. The only there is celery thing is there, which has some issues with that, Redis being single point of failure for us as of now. And we wanted to move to more containerized based environment, which is Kubernetes executors, right? So that is the reason we want to move from celeries, right? And not want to invest more into solving those single point of failures. We could solve those things as well, but rather than solving one thing and again moving to something, let's say Kubernetes, right? We're directly moving to Kubernetes. So, but of course, like eventually in this container also, the task will run as a Python only, right? That it will be a Python task which will be executing that pipeline. So it will be Python task only. It won't be like, we are no plan to convert everything into Java or like converting the DSL, the user written Python into pipelines into Java or anything like that, right? Only a small service.
I got my answer. Thank you.
Cool. I think that was really interesting. A lot of good questions. Thanks a lot for staying up so late. Really appreciate it. And a shameless plug, Uber is hiring, right? So yeah, feel free to reach out. Yeah, thanks.